Look at the surface unraveling on screen. We have a highly distorted, nonlinear mapping. Under what conditions can we force this to behave like a simple, flat, linear projection? The rank theorem guarantees we can find a localized neighborhood where the distortion completely flattens out. To see exactly how this works, we need to consult the definitive text, Walter Rudin's Principles of Mathematical Analysis, often referred to by students simply as Baby Rudin. Specifically, we are looking at Chapter 9, which covers functions of several variables. Tucked away in this section is the formal statement of the rank theorem itself. Mastering this theorem is the critical bridge. It takes the isolated tools of basic multivariable calculus and integrates them into the foundational language of advanced differential geometry. You already know the standard tool for measuring the local behavior of a multivariable mapping, the Jacobian matrix. It acts as the multidimensional derivative. Generations of mathematics students have sat in lecture halls grappling with the limits of this matrix. When the Jacobian has full rank, meaning its rows and columns are entirely linearly independent, everything works perfectly. We rely on the inverse and implicit function theorems to guarantee our mappings are well-behaved and locally invertible. But a problem arises when a mapping drops dimensions. If the Jacobian matrix becomes singular, lacking full rank, those standard theorems fail. The mapping might fold, cross itself, or collapse entirely. The rank theorem provides the necessary structural guarantee. It tells us precisely how these mappings behave when standard invertibility fails, provided one critical property remains constant. This 3x3 matrix has column vectors that span only a two-dimensional plane. The dimension of this space is its rank, here rank 2. Watch if the rank drops to 1. The plane collapses into a line, creating a singular point. To handle these singular points, we need a mathematical tool called a diffeomorphism. This is a smooth mapping that is completely invertible, and its inverse is also smooth. Think of diffeomorphisms as coordinate grid benders. As this Cartesian grid smoothly morphs into polar coordinates and back, notice that no lines overlap and nothing tears. The fundamental topology is preserved. These grid benders act as our conceptual lenses. By applying the right diffeomorphism, we can straighten out singular, nonlinear behavior without breaking the underlying space. Our objective? Find local coordinates where function f becomes a simple linear projection. Algebraically, g of f of h inverse of x equals L of x. H inverse domain straightens the input grid, while g flattens output curvature into a purely linear projection. But there is a strict prerequisite for these lenses to exist. The rank of the derivative cannot just be evaluated at a single point. It must remain perfectly constant throughout the entire localized neighborhood. If the rank fluctuates, the physical structure of the space breaks down. A smooth domain will suddenly pinch, crease, or fold upon itself. Smooth coordinates can no longer be drawn across a sharp tear. A constant rank is the absolute geometric necessity. It prevents these topological folds, guaranteeing that our space remains workable for our straightening lenses. With the geometric intuition clear, we can decode Rudin's algebraic proof strategy, which relies entirely on manipulating the Jacobian matrix. Step 1. We reorganize coordinates so the Jacobian's top left forms an r by r square block. Assuming constant rank r, this block's determinant is non-zero and invertible. Step 2. Rudin constructs a temporary mapping applying f to the first r coordinates, forming identity blocks below. Step 3 focuses on this new construct. Because the matrix is non-singular, we apply the inverse function theorem. The output isn't an abstraction. It collapses to give us exactly h, the domain-straightening diffeomorphism needed for our equation. This is the elegance of Rudin's approach. He uses strict block matrix algebra to explicitly carve out the geometric lenses whose existence we visualized earlier. Take a final look at this complex manifold. As we zoom in, the nonlinear curvature vanishes, leaving a surface indistinguishable from a perfectly flat plane. This principle dictates the boundaries of physical engineering. Robotics engineers rely on the rank theorem to avoid kinematic singularities, the specific configurations where a robotic arm drops rank and suddenly loses a degree of freedom. In theoretical physics, this same mathematics defines valid phase spaces, ensuring that physical systems obey their conservation constraints without mathematical collapse. Maintaining this constant rank ensures that the degrees of freedom in a physical system remain stable. It prevents the system from encountering the pinching or creasing that marks the limit of smooth coordinate control. To recap, the Jacobian matrix captures local multivariable behavior, and maintaining a constant rank is what prevents topological tearing. By verifying that constant rank, the theorem provides a local normal form, effectively extending the logic of the inverse function theorem to include singular mappings. The power of local linearization lies in finding predictable, perfectly flat simplicity hidden deep inside global complexity. To continue decoding the mechanics behind classic mathematics, leave a like on this video, subscribe to the channel, and turn on notifications for our next chapter-by-chapter textbook breakdown.